Well, hello again. Hopefully, you guys are all doing okay. It was good to see that you did really well on last week's quiz. One of the problems you had last week was one that Iowa Lakes requires that we ask you, and that's one of the ways that they evaluate that you do as well as the people that take the course on campus. And since you guys all got a perfect paper last week, you definitely are doing fine with it. We've, of course, been talking about various kinds of optimization. We started off with some physics problems, and then we went on to some geometry problems. And this week, we're going to expand that and talk about optimization in problems that involve business. You should remember from last week that to do an optimization problem, you always found an objective function. That was the thing you wanted to maximize or minimize. You found a constraint equation. That was something that set limits on things so they couldn't just go on forever. And the key to the whole problem is you took the derivative of the objective and that had to equal zero. Well, it turns out that same basic process is going to happen in these business problems. And if anything, they're actually quite a bit easier than the geometry ones because basically you do the same thing every single time. I'm going to start by showing you two problems that are examples of what these look like. We're going to look at the problems, then we're going to come back and figure out how to do them. So the first problem we're going to look at is one I wrote myself back in the 90s, and I wrote it right after we had gone to our very first trip to National Quiz Bowl, which happened to be down in Dallas that year. And the very first game that we played at Nationals was against a school named Holy Family High School, which was from Grosse Pointe Woods, a suburb of Detroit. Now, Detroit is one of the poorest places in America, but Grosse Pointe Woods, which at one point was the home of Henry Ford, is actually one of the wealthiest suburbs there is in the country. And the kids from Holy Family were some of the most stuck-up people I have ever met in my life. They looked at our team and they saw a bunch of hicks from rural Iowa, and they were pretty sure they were just going to walk all over us. It turns out that in that game, we won by 5 points in overtime. And because we ended up winning that game, on a question about The Simpsons, ever since then, I've always put a question about The Simpsons in the tournament we host every October. Well, in a way, there's actually some revenge on Grosse Pointe Woods and Holy Family as well, because Holy Family High School no longer exists. The Diocese of Detroit actually combined their schools, and now this high school was closed and combined with about three others to make a school that today has fewer students than that one high school had back in the 90s. But that's the background for it. We're going to go through and talk about what the problem says. Tells you that this high school back in the 90s charged an annual tuition of $13,450 per year. Now, even today, that's many times what we charge at Garrigan, but if you went up to like the Twin Cities, you'd find that the Catholic schools up there do charge tuitions in that range. Back in the 90s, Holy Family had 587 students. Key to the problem is this next part. It says they found that for each dollar they increased the tuition, they would lose a fourth of a student. And I did totally make that up, but obviously their enrollment has gone down a lot since then, down to zero, and so they have been losing. And the question is, what tuition should they charge to maximize their income? So the next problem is actually about a gentleman who did the problem about Holy Family High School back when he was in high school. Brad Nelson graduated from Garrigan back in 2001, and he took calculus back when he was a senior. And he went on to play professional baseball, which would be what this problem's about. The problem was actually written by his classmate in calculus, Ben Lichtai. Ben went on to be an optometrist, and now he's a very successful optometrist in the Boston area. And what the problem says is everybody wants a Brad Nelson bobblehead doll, but only if they're cheap enough. If they make 5,000 little Brads, they can sell them for $14.98 each. However, for each additional doll they manufacture, the price will need to be reduced by 2 cents. What number of bobbleheads will they have to make in order to maximize their income? So the first one, we wanted to figure out what was the ideal price they should charge. This one, we want to maximize the income. Something that's kind of nice about these business problems is that they really are kind of all alike. The objective function that you use every single time says R equals NP. What that stands for is revenue equals number times price. Would be like if the bobblehead company wanted to maximize revenue, they'd have to figure out how many do they make and how much do they sell each of them for. The revenue equals the number times the price. Technically a couple of possibilities for what the constraint equation could be, but they're very similar to each other. You notice the first one says N equals N0 minus D times P minus P0. And the second one, it just switches around N and P and says P equals P0 minus D N minus N0. So what N and P, of course, stand for is number and price. N0 and P0, you might know from like a physics class, the 0 means the initial amount. So like the initial number or the initial price, how much you know at the start of the problem. D is always a change per unit. It's a difference per unit, and that's typically either given in the problem, which it was in both of these, or it's going to be something that's very easy to figure out. We'll talk about how you figure out which of those you look at, but it's essentially the same thing, just one of them solved for number and one of them solved for price. So back to our problems. On the first one, it told us that Holy Family High School, back in the 90s, they charged $13,450. That's going to be the starting charge that we have. They also started the problem with 587 students, and they found that for each dollar they increase tuition, they lose a quarter of a student. And that means they're telling us in this problem that the initial price, the P0, is $13,450. The initial number is 587 students, and the difference, the change per increased unit, is 1/4, or 0.25. Those are all just taken straight from the problem. Again, the two possibilities for what you could use for an equation, one of them begins with N and the other one begins with P. The way we tell which one to do is we look at what the question's actually asking. This problem says what tuition should they charge to maximize their income. Whatever that says, I always choose the equation that says the opposite. So it's asking here about the price. That means I want the N equals equation. The reason why I choose the opposite one is that I'm going to replace that variable, and then what's going to be left is just price. So our objective is going to be R equals NP, revenue equals number times price, and our constraint will be N equals 587, the amount we start with, minus 1/4, or 0.25. That's how much it changes per dollar. And then P minus 13,450, the price or the tuition that they started with. So just like before, we want to simplify the constraint as much as possible before we substitute into the objective. And here I distributed out the parentheses. I basically took negative 0.25 times both of the things in parentheses. When I do that, I do get a plus on that term at the end because it's negative times negative. And then I took that term at the end and I added 587. I combined like terms, and that's where I'm getting N equals 3,949.5 minus 1/4 P. And the next step is substitute into the objective. Well, our objective was R equals NP, and we just figured out that N was equal to 3949.50 minus 0.25p. So I just changed the N in the problem to that expression. And if you distribute that out, you end up getting 3949.5p minus 0.25p squared. What I've always got to do, of course, is take derivative equals 0. Well, the derivative of that is just 3949.5 minus 0.5p. You set that equal to 0, and it's not terribly hard to solve that. You just divide by a half, and you get that their ideal tuition would be $7,899. Now, since of course they were already charging way more than that, that would mean they'd have to slash their prices dramatically to make the most possible income. Sometimes people will wonder, how is it that you get a smaller amount than they're charging now as the ideal tuition? Well, the idea is that if they charge less, they would actually attract more students. And while each of them would be paying less, the grand total, when you multiply by that additional number of students, would be greater. So here's that other problem about Brad Nelson. And I want you to look through that and see if you can identify what the different variables, the P0, N0, and D, would end up being in this problem. You should find that the initial price given in the problem is $14.98. The initial number is 5,000, and the difference is 2 cents because for each additional bobblehead they make, they have to lower the price by 2 cents. So those are all given in the problem, and I put them down there. I did, by the way, put the picture of the other bobblehead of Brad Nelson, which was from the High Desert Mavericks out in Adelanto, California. And just to get an idea of how unrealistic this problem is for a minor league team, when Brad actually played, there were 500 bobbleheads of him produced by the White Snappers and 1,000 produced by the High Desert Mavericks. So both of those are way less than what this problem says. The question this time is, what number of bobbleheads will maximize their income? And since the question asks about the number, that's why the constraint we're going to use is P equals. Again, you always go for the opposite variable. And here we'd have P equals 1498 minus 0.02, quantity N minus 5,000. Again, initial price minus the difference, and then N minus the initial number. I simplified that just like last time. I distributed out the parentheses. You always want to be careful that is a plus at the end, and it always will be. And then you add that on to the initial price at the beginning. So 114.98 minus 0.02 N. The next step, of course, is substitute into R equals NP. Basically, what always happens when you do that is you're just multiplying everything by N. If you had one of the ones where you had done an N equals problem, you'd end up multiplying everything times P. But you just basically take what you just got, simplifying the constraint, and you multiply it by the other variable. Key step is always derivative equals 0. Here the derivative would be 114.98 minus 0.04 N. To solve that, you just divide by 0.04, and it turns out that we get an answer of 2,874.5. Now, that is an impossible number of bobbleheads to manufacture, and if you do get a fraction answer, what you want to do is pick what's closest. In this case, we're actually equidistant between two different numbers, and what that means is they could maximize their profit by either doing 2,874 or 2,875. Either of those would give them the maximum profit. Now, in the real world, the price of bobbleheads actually has the most to do with how successful players are rather than how many were manufactured. And the year that the Snappers bobblehead was made of Brad, he actually was the Brewers minor league player of the year. And at that time, that bobblehead was worth as much as $150. Today, I just actually searched when I did this PowerPoint on eBay, and you can see you can get it for 28 bucks basically. And that actually is not a bad number. It's been worth as little as 10 bucks, but it really doesn't have a whole lot to do with the quantity. It's more with the fact that he was successful in the minor leagues, but then didn't do real well in the majors. Again, in revenue or business problems, your objective function is always R equals NP, revenue equals number times price. And the constraint is always one of these two, and you choose whichever one begins with the opposite of what the problem is asking. We're going to look at one more problem and then wish you well. So our last problem here deals with gala. And here you got a couple of pictures that are actually from this year's gala. This year's gala, of course, was a virtual event that happened completely online, and it's really kind of amazing that the total that they took in was $285,000. While that is about $100,000 less than last year, it's a ridiculously large amount of money given the circumstances, so we should all be very thankful for how well that went. The problem, which was written by somebody a few years ago in class, would deal with the more traditional setup of gala. It tells you that at gala there are approximately 350 guests, and they spend an average of $900 per person. I'm pretty sure the person that wrote this problem just made those up, although it's not too far from the truth on what things would be. Goes on and says some people complain that it's too crowded at gala, which is definitely true. And it says, suppose that for every additional person who attends gala, each guest spends $17.50 less, and it turns that around and says that for each fewer guests, they'd spend $17.50 more. What would be the ideal number of guests to invite to gala? Now, what's said in this problem is actually implied in every problem like this, that a lot of times it says as something increases, the other part of it goes down, but you could also say as the first thing decreases, the second thing's going to go up, and it does work in both directions. Let's look through this one. Right now it's telling us that people are spending an average of $900 per person. The initial number was 350 guests, and the difference, the amount it's changing by, is 1750. Since the question asks for the ideal number of guests, that's why I do the constraint that says P equals, so P equals 900 minus 1750 times the quantity n minus 350. Again, you simplify that as much as possible. You substitute into the objective, which basically means I just multiply both parts times n, and then I do derivative equals 0. And this one, what our ideal answer would end up being is basically 201 guests would be the whole number of guests that would come the closest to our possible answer. And again, they'd have fewer guests, but each of them would actually be spending more money, which is how they would end up maximizing their income. So on the website, I do have a little worksheet that's got 10 problems, just like the ones we just did, that you can use to practice. And I'll put the answers to that up in a day or two. And like last time, I'm going to ask you to do 2 problems instead of the online quizzes that we've done. And I want you just to show your work, and then you can send those back to me. I think all of you did that just with pictures last time, and that worked great, so no problem at all with those. Mrs. Peterson had told us that she wanted us to try and have everything due by Wednesday this week so you guys could have a long Easter break. If you want to get it done by Wednesday, that's great. If you want to procrastinate, that's okay too. Realistically, any time before next week will be fine from my point of view on it. And with that, we'll call it good for this week. I do hope you are doing well and that you do have a happy Easter. Take care.